So first of all, thanks for having me and thanks for this kind introduction. Of course, thank you for your interest in my talk about Python or using Python to unit test smart contracts or Ethereum smart contracts. Can you hear me all right? Okay. So yeah, as said, in my professional life, I'm a data scientist at Flixbus. So usually I do machine learning and time series analysis and price optimization. But about a year ago, I got infected by the cryptocurrency fever, as some people did. And in my spare time then, I played around with blockchain technology and one technology in particular, and that is Ethereum, because Ethereum is pretty cool. It's a blockchain you can actually program. And just to emphasize this again, so I do this in my spare time. So I'm by no means at all an expert on Ethereum smart contracts. So if you really think about releasing some Ethereum contracts into the wild, meaning deploying to the mainnet, feel free to approach me and we can talk about this, but please seek expert advice, right? Because we will see later on, it's very, very easy to lose a lot of money on the blockchain, especially other people's money. So, yeah. But before digging into what Ethereum is and how you write smart contracts and how you can actually then test them in Python, let's start with the very basics. So Ethereum is a cryptocurrency which is based, as many others, on blockchain technology. So what is a blockchain? In simple terms, a blockchain is nothing else but a distributed database where you store so-called facts. So facts are just pieces of data that have been verified to some extent to adhere some certain rule sets that apply to this particular blockchain. And these facts, these pieces of verified data, are bundled together in so-called blocks. This would be then the first block and then the second block, and as the name suggests, they are kind of chained together. So they are linked sequentially, and you can actually count them. So like the first block is usually the genesis block. And the way they are linked is usually by hashing. So what you do is you attach pretty much a label to each of these blocks. And the label is the hash of the contents. So the genesis block, for example, you would somehow take the contents, hash them, and this would be the unique label, such as like for a git commit, that identifies this block. And then the linkage between the blocks is actually established by not only hashing the contents, but also taking the hash of the previous block in your hashing operation. And you can do this then in subsequent steps, and by this you form a chain. And as I said, this chain is shared across very different nodes in the network, usually a couple of thousand nodes, and all of them keep an exact same copy of this blockchain. Sorry. And most of the complex and involved part of blockchains is about actually getting new data into the blockchain and making sure that then still everyone has the exact same copy of this blockchain. So there might be some free-floating facts that haven't been checked yet, but that want to become part of this blockchain. And there are certain people who take care that new data can be inserted into this distributed database. And these are the so-called prominent miners. So the job of the miners is to actually collect, verify, and combine new facts into new blocks. And then once they come up with a new block, they have to do the so-called proof of work. So the proof of work essentially is just a very expensive computational operation just to make coming up with new blocks very, very difficult. And we'll see in a minute why we need this. And these miners are not doing this for the good sake of mankind, but they do this because they get rewarded for it. So there's some monetary reward in for them for actually creating new blocks. And then they can actually publish new blocks, and we can extend the blockchain. And there might be other nodes in the network as well, which are not necessarily miners, but they could be passive nodes. And their job is then just taking these new blocks and actually verifying that also the miners did a proper job, and that they verified the data correctly, that they came up with the correct proof of work, and so on. So what is this mysterious proof of work? This mysterious proof of work is also based on hashing. So the cornerstone here is cryptographic hash functions. So a cryptographic hash function is simply a function that takes an input message M of arbitrary length and digests it to a fixed length output, here D. So usually, let's say 256 bits, so just a stream of zeros and ones. And what is so beautiful about these cryptographic hash functions is it's infeasible to actually revert this operation. So in order to come up with a D that has a particular shape, the only thing you can do is actually brute force trying to guess different messages that you put into this cryptographic hash function. And actually, this is what miners have to do when they solve the proof of work. So basically, the proof of work states that, dear miner, you're allowed to change the message as you like, but you have to come up with a hash digest that is small enough, or you might think of it as that has a sufficient amount of leading zeros, right? And this is incredibly complicated because sometimes this can be up to 40 leading zeros. And the message the miners are allowed to put into this cryptographic hash function consists of two parts. So the first one is called the challenge. This one's going to be fixed. But the other one is called the proof. So this is the one they can actually, in a brute force manner or iteratively change in order to guess a good hash digest. So this could be just the integers that they start counting, 1, 2, 3, 4, and so on. And this is all the proof of work is, just trying to guess an input to come up with a hash digest that has the sufficient amount of leading zeros. And usually this is, as I said, quite expensive, so there might be billions and billions of hashes involved that they need to compute. Okay, so how does it now work if a miner wants to produce a new block? So let's say our current head of the blockchain is block K, so this is the newest block that is available, and there are some free-floating facts around. And the first thing the miner does is actually verify the facts. So he checks that these facts adhere to the rule set at hand. And once he's verified the fact, he's allowed to create a new fact for himself. Because as we said, they are rewarded for this. So they can create a new fact that somehow states this miner is rewarded for his work. And then he takes all the facts, pairs them, concatenates them, and pairs the hashes. And hashes the pairs of these facts. And then he takes the hashes of the hashes, pairs them, and hashes them. And he does this until he leads to such a root of such a hashing tree, which is also called Merkle tree, which is then pretty much the hash of the content of this particular block he's going to produce. And then he takes the hash value of the previous block, combines it with the hash of the contents, and hashes it again. And this is then going to be, so the hash value of this combination is then going to be the hash value of this block. So this is then the label that is attached to this block, and it's also going to be the challenge string for this proof of work. So far this was already a lot of hashing, but now comes the actual involved part, like now starts the real hashing, because now the miner has to come up with a proof of work that combined with this hash value of the block actually gives a hash digest that has a sufficient amount of leading zeros, let's say 40 leading zeros. The exact amount of leading zeros actually depends on the blockchain at hand. So for example, for Bitcoin, this is dynamic and is chosen such that on average every 10 minutes a new block is produced. And once he succeeds in actually finding an appropriate proof string, he just publishes the new block and the proof string to the network, and then everyone else can actually check that the miner did a proper work. So he would go along, hey, other nodes in the network, I found a new block, I found the appropriate proof of work, here is a new block, and then everybody would again check that the miner did a proper job, which means are the facts true, is the proof of work true, and if that's the case, then we entered new data into this database. And this is how you extend then the blockchain. So what are these facts actually? So for Bitcoin, these facts are just transactions, right? So facts could be something like Alice sends 20 Bitcoin to Bob, or Bob sends 60 Bitcoin to Charlie, or facts could be stuff like new 50 Bitcoin to Alice because she mined this block and she's rewarded for this. So she can create Bitcoin out of thin air. And checking these facts just now involves making sure that the people spending money actually have the appropriate funds to do so, right? So if Alice wants to send 20 Bitcoin to Bob, in order to verify this fact, a miner has to check that Alice actually owns 20 Bitcoin. You might wonder, okay, so miners have to check transactions. That makes sense, right? Because people shouldn't spend money they don't have. But why do we need this expensive proof of work? This is so wasteful, that is billions of hashes that cost so much energy. Well, the reason is this is sort of a replay protection, and this is actually the cornerstone of the blockchain that makes it secure. Because assume that the proof of work was not expensive and we could easily create new blocks. Let's say Alice and Bob meet and negotiate over, let's say, a car for 50 Bitcoin. Then Bob gives Alice the car, Alice sends 50 Bitcoin to Bob. Everyone's happy because Alice owns the car, Bob has 50 Bitcoin. But now Alice is mean and actually creates just new blocks right before this block where the transaction to Bob was mined. Because in this hypothetical example, creating new blocks is easy because there's no important or difficult proof of work. She could simply start overtaking the blockchain with new blocks and thereby pretty much rendering this transaction invalid, or from the perspective of the blockchain, this transaction has never happened because the protocol dictates that the true blockchain is always the longest blockchain. So in this case, then, she would actually have the car and the 50 Bitcoin, and Bob, well, he lost everything. And this is the reason why we need this expensive proof of work to make this situation pretty much impossible. Okay, so this was the basics of blockchain. Now let's move over to Ethereum. So Ethereum is pretty much similar as the stuff we've seen before. So it's very similar to Bitcoin. It's also a cryptocurrency. There the units are not called Bitcoin, but simply called Ether. And it's also, as we've seen before in this blockchain example, it's just a distributed database. But the difference is now what we can store as these facts into this database. So for Bitcoin, we've seen these facts are just transactions. But for Ethereum, the new thing here is you can, of course, store transactions, so you can send around this Ether, but you can actually store arbitrary data into this blockchain. And arbitrary data means you can actually store executable code. So you can write programs onto this blockchain, and these programs are called, in the terminology of Ethereum and other cryptocurrencies, are called smart contracts. So pretty much then, so these facts that now can be stored on the database can be summarized as transactions, bytecode of compiled programs, and of course persistent data. So pretty much this is how the Ethereum blockchain looks like. So the Ethereum blockchain now lives in this so-called Ethereum Virtual Machine, which means whenever you deploy stuff to the blockchain that is a program, that gets executed by the miners and other nodes within this sandboxed Ethereum Virtual Machine. So a blockchain might look like this. So in the Genesis block, Alice mined this block, so she gets a reward, 50 Ether for this. And of course, you can have transactions as before, like sending around Ether. So like Alice sends 20 Ether to Bob. But now the new stuff you can do is there might be transactions that go like this. Alice deploys the bytecode of the program that she's written that is called slotmachine.sol. And from then on, this program lives on the blockchain and can be used by other people. So there might be some later interactions with the blockchain of other accounts and other users. So Bob might actually send 3 Ether to this smart contract and call the function pull lever, because he might want to win some money, but he loses, and then the 3 Ether are stored by the contract and could maybe later be withdrawn by Alice because she wrote the contract. Okay. So what is now the job of the miners in Ethereum? So it's actually very similar to what we've seen before. So of course, their job is data collection and verification. So they have to check Ether transactions, so they have to make sure that people who spend funds on the blockchain actually have the appropriate amount of money available. But also they have to execute contract code in the Ethereum Virtual Machine, and this might incorporate stuff like creating new contract instances. As we've seen before, Alice deploys the slotmachine.sol. It might be other people actually executing functions on these contracts. And during these functions executions, actually the persistent state of these contracts might change. So for example, in this pull lever function call we've seen before, you could have a persistent state variable that just counts how many people actually pulled the lever already, and you would just start counting whenever somebody pulls the lever, and then this state variable, which is just an integer, would be persistently stored on the blockchain, and every time increased somebody pulls the lever. And then, again, they have to do the proof of work, and of course they get rewarded for doing this expensive calculations. And finally, once they succeeded in doing the proof of work, they of course have to again publish the new block, and then all the other nodes have to check that the miners did a proper job. So Ethereum brands itself as the world computer, which it kind of is, because basically your program gets executed by a lot of people, but it's a very inefficient one, because these nodes checking that the miners did a proper job also have to re-execute the code. So whatever you deploy to the blockchain is going to be executed thousands of times, just to make sure that your program does what it's supposed to do. Okay. Let's come to the actual programming part and doing stuff on the blockchain. And first disclaimer, contract programming is incredibly hard. The problem is once you deploy to the blockchain, actually updating stuff is close to impossible. And because of this, there have been, there's a almost infinite list of errors that people coded into their programs that led to loss of millions and millions of dollars. And I just picked two, the most famous ones. So the first one is the so-called DAO hack. So DAO stands for Digital Autonomous Organization, and it's pretty much like a Kickstarter implementation on a blockchain. So you could transfer funds to this DAO smart contract, and then this DAO smart contract would fund other projects. But also, since you could send money there, you could also withdraw your money. And somebody actually managed to withdraw all the money by a recursive execution of a function. And this exploit wasn't known at that point in time. And so when this guy did, about 50 million US dollars at that point in time were lost, which corresponded to 15% of all Ether in circulation. So that was a big flaw. And actually, because it involved like more than 10% of the Ether, something very revolutionary happened. Because the entire Ethereum community came together and said, we can't let this happen. So what they did is they actually rolled back the blockchain, fixed the bug, and said this transaction never happened. So there was like a massive social consensus all over the internet across lots of different and also anonymous people, except for like a small group of people actually were very pissed about this. And they said, you shouldn't do this, you shouldn't roll back blockchains, code is law. And because of this, a second cryptocurrency was born, Ethereum Classic, where they kept this transaction and where they said, okay, so we're the rebels here and we're just going to have our own cryptocurrency now. There was another big hack more recently, which is called the parity funds freeze. So parity is a smart contract that just instantiates a wallet. So pretty much it just stores Ether for you in a kind of more fancy way with a bit more tools around it. The problem was that somebody with a GitHub name DevOps1999 was actually able to took ownership of a library that was powering this wallet, and then just by executing functions on the blockchain was able to kill that library and make it unusable forever, like it's dead. And as a consequence of this, everybody who used these wallets can no longer move their funds. So by the point in time, that was 150 million US dollars. So probably nowadays it's even more. And because, I mean, the cryptocurrency space got a bit bigger and there's more money involved, this is no longer on the order of 15% of Ethereum in circulation. So this actually did not justify for a rollback of the blockchain. So these people are, well, their money is stuck, probably forever. Yeah, so as I said, contract programming is hard, and it's very easy to make very costly mistakes. So testing is of utmost importance, probably even more important than in the regular IT world. But, and the beauty here is, you can do this in Python for Ethereum smart contracts. And this library is called Populous. So if you manage to pip install Populus, which is still kind of developmental, so there might be a few hiccups, but let's assume you actually managed to install this library, and then you call Populus init on your command line. What it will give you is a hello world example of an Ethereum smart contract and their hello world example of how to test it. So, so this is then the example they give you. I don't want to go into details, but what you can see here, this is the Solidity language. So this is the language of choice to write smart contracts for the Ethereum blockchain. It looks a lot like and has been heavily inspired by JavaScript. So I'm sorry about this. But the good news is the testing part of it can be done in Python with the Populus library. And this is exactly what we want to do now. So I just want to quickly code up with you a little game that we're going to play on the Ethereum blockchain and write the corresponding tests to it. So like little live demo. They always tell you don't demo. Let's give it a try. Hi. Okay. Can you see this? Should I make it a bit bigger or? Ah, yeah. Is that big enough? Okay. I mean, even if I mess it up right now, I have all the stuff prepared, so I can just go the full TV chef. I have something prepared for you here. So, okay. So let's write our first smart contract, this little snowballs game I have in mind. And the game is actually very silly and very easy. So what we want to do is create a game where you can throw snowballs at other people. The only thing that happens if you throw a snowball at someone, he's going to keep that snowball and is able to throw snowballs at other people. And also you get rewarded for just throwing snowballs with more snowballs. Okay. So as I said, contracts are called, programs are called smart contracts. So in order to start a smart contract, the keyword here, of course, is contract. And then we give it a name. And like the Python analog here would be simply a Python class. If you then deploy to the blockchain, pretty much your instantiated contract then corresponds to a Python object. And similar to Python objects, you can have, of course, attributes or state variables. And let's just add one state variable called mapping. So a mapping is pretty much like a dictionary in Python, but a very bare-bone one that just has a default value of 0. So if the key is not present, then the corresponding value is just going to be 0. And we're going to have one mapping from addresses. So this is just like users of the blockchain to integers. And let's call this balances. So this is just going to be a mapping that stores the amount of snowballs somebody has, right? And then, as most Python classes have, we need an init function, which in the very new forms of Solidity is called constructor. And it just goes like this. So what are we going to do when we initialize this class, which just means we're going to deploy it to a blockchain? I think it's just fair that if I just get 100 snowballs. I mean, I invented the game, so this should be fair. So there's this keyword message.sender, which is always the guy executing the function. And the constructor can only be executed by me once I deploy it to the blockchain. And I'm just going to get 100 snowballs. So now we've written our first contract, which is pretty silly because the only thing it does is giving me 100 snowballs. But let's start with the first test. Oops, that's the wrong file. Let's start with the first test of this. So let's just test if we actually succeeded in giving me 100 snowballs. Then we can use simple PyTest functions, which just start with the word test. Right? And now comes the beauty of Populus. So Populus already gives you a lot of fixtures that you can use in your code. And one of these fixtures, the testing fixtures, is the so-called chain. So basically what Populus does is creating an in-memory blockchain for you that you can use. So we can now deploy to this blockchain. Populus will take care of all the nitty-gritty details like miners mining stuff, collecting transactions, verifying transactions, and the only thing we have to care about is our contract. Another nice feature it provides is the so-called accounts. So it will create 10 accounts for us, and the first account is just going to be me. Okay, let's deploy this to the blockchain using Python. So we can do it like this: chain.provider.get or deploy contract, and we have to give it the name of the contract. Did I write it with an S or without? Without. Snowball. And then we can write our first test. And the only thing we have to test is that I get the appropriate amount of snowballs, which is just my contract. Please check if I ask for the balances of me, which is the first account, this should be 100 snowballs. And let's see if it works. And hooray, it works. I'm actually surprised that it works the first time. So we've written our first test, and we've seen that, okay, so I can assign myself 100 snowballs. Let's do one more thing and extend the contract to actually incorporate parts of the game. Let's create a function where you can actually throw snowballs. Okay, so let's call this function throw ball, and it takes one parameter, the target user, so the guy I'm actually throwing snowballs at. And of course, we just want to make sure that only people can participate in the game who actually own snowballs. So you can use this nice require statement, which checks for Boolean conditions that have to be true in order to execute this function. And as I said, we just want to make sure that the guy, whoever calls this function, so again, this is this message.sender, has the appropriate amount of snowballs, so has at least one snowball. And yeah, JavaScript, so we have to stop with a semicolon. And then parts of the game then are that me, or the guy throwing the snowball, is rewarded with more snowballs, let's say 2, but also the guy who got hit is rewarded with a single snowball. So he got to keep the snowball. So this is now our game. Let's write one more test for this. Huh? Oh, yeah, pub. Thanks. Yeah, we need this keyword, otherwise people can't call this function from the outside on the blockchain. And there we go. Let's create a new test. Define test throw ball. Again, we use the blockchain, we use the accounts. And I'm just going to copy and paste this deployment here. Okay, so now throwing a ball is actually a transaction on the blockchain. So now we have to say, please, dear contract, transact the following transaction, which is just throwing the ball. Transact. And this is the function that we now call on the blockchain, throw ball. And let's take as a target the second account. And then now, because this is an actual transaction that's carried out by the blockchain, we have to wait until it's mined. And you can do this with the following statement, chain wait for receipt. And please wait for this transaction. And this should actually then wait until we throw the snowball. And it's by default, so you can actually pass a dictionary here where you can set who is the thrower, but by default it's going to be account 0, so the first of the accounts. And let's write just one test that actually the guy we throwed at now owns a snowball. Call balances. Okay, so let's see if our test succeeds. All right, it does. So it works. So what we just did is deployed the our little game to this in-memory blockchain, and then we threw a ball, which is a transaction, and then we checked that the guy we threw the ball at actually has one new ball. Okay. Can you check that you have 2 more balls? Yeah, we could, of course, we should check that too. But in the interest of time, I'll leave that as an exercise to the reader. There's one more thing. So with coding up this very little game and only these few lines of code, I already introduced probably a big error into this game that can be exploited by players. And this is, I didn't check that I throw the stuff at myself, right? So I could just exploit this and then throw snowballs at myself, and I would instantly get 3 more snowballs, 3 more snowballs. And this is probably not what this game is about. So you've seen, even with a few statements, we were already able to create a big mess. So if I actually had deployed this to the real blockchain and already had some people playing the game, and then I realized, oh, I have to fix this error because I don't want people throwing at themselves, the only way to fix this would be to create a new contract, deploy it, and then convince all the gamers to move from the old game to the new game. Okay, sorry. That's pretty much about it. There's a few take-home messages. So first of all, just as a short repetition, so Ethereum is a super cool cryptocurrency that allows you to run so-called smart contracts on a blockchain. And then we've seen there's this nice populous library that you can use to actually test these smart contracts in Python. Actually writing good Solidity code is incredibly difficult, and it's super easy to introduce errors that are very, very costly. So that's about it. Thank you very much. There is a few references here. So there's the link to the Populous library. There's documentation of the language. There's a cool IDE that you can use in your web browser where you can actually instantly deploy to the main or to the testnet of Ethereum. There is the MetaMask browser plugin, which you should check out because that's a very nice way to interact with the blockchain directly in your browser. And there's this nice list of Ethereum hacks, like there's tons of them, where people made very costly mistakes, and it's a very nice read. To contact me, just drop me an email or visit my GitHub profile. There's actually, so I deployed this game to the real testnet, a bit more comprehensive version of this game if you like to play or figure this out. I'm also, you can find me on Steemit, which is a social media site that's actually operating on a blockchain. And of course, Flixbus has a booth here. So if you're interested in cryptocurrencies, come to me. If you're interested in getting hired as a data scientist in machine learning, also come to us and talk to also other nice people at the booth sitting there in the back. Thank you.
Thanks a lot for this great talk. Really interesting topic. So we have plenty of time for some questions. Any questions?
Thank you. I have just a couple of questions. The first one is, what if the result of the program is different between miners? What is the right choice? Because you told that the program will be executed by all the miners around the world.
It cannot be. So it's living in this Ethereum sandbox. So they all should come to the same conclusion. If some miner actually computes something else, then it's a faulty transaction and it's not going to be part of the block.
If the program is doing something randomically, like your slow machine,
yes.
How does it work?
That's a good question. There's no pure randomness on the blockchain. There are, and this is a very difficult topic to actually getting random numbers into the blockchain. So the easy way could be just taking the hash of the block as a random number, but the problem is then the miners can actually use and exploit this. So there are ways of so-called oracles where pretty much users send random numbers to the blockchain as transactions, but there's no pure randomness in the blockchain. So in principle, everybody should come to the very same conclusion executing the same program.
Okay, so the slow machine game cannot be in the
No.
Okay. Second question is, how can you kill a library? The second act that you show us. You cannot release a new version of the library and then restore the wallet.
So some of the libraries support, or some of the smart contracts support something that's called self-destruct, which pretty much just makes it unusable. And this guy, DevOps1999, actually took ownership. So there was a function, claim ownership, which hasn't been done by parity. So the ownership was never claimed, so because they forgot about it. So this guy claimed it and then called self-destruct, and then it was unusable. And yeah.
Okay. Thank you very much.
Thanks for the talk. I have a question. You said that upon running the smart contracts, there's a change of state, and I'm asking myself, how can the blockchain change state and still remain valid? Or is that not, like, where does it change?
So pretty much, so the state change, for example, would be you have a state variable that is just an integer, right? And you just increase it by 1. This could be a state change. And the state change is, of course, initiated by a transaction. So if you really think about it, all the states have been there. So when you initialized it as 0, this was a transaction. And then if you added 1 to it, this was another transaction. So you could pretty much replay this.
So it's like a linked list then?
Yeah.
Yeah, thanks. Are you able to use Populus in an interactive way with IPython Notebook, for example, to actually play something sort of interactively?
I haven't tried this. Sorry, okay. I can't answer that. Okay.
Are you working on any other smart contracts with right now?
Not recently, but I actually wrote a smart contract where you can sell your soul on the blockchain.
Okay. Sounds fun.
Yeah, so far I only did some silly projects like this snowball game. So.
Hey, thanks for the talk. As I see it, like blockchains are trying to decentralize not have like one authority in the center who controls everything. So you have like a lot of different parts who control it, and like this is testing that like this in the Solidity frame, like the code is correctly executed and it's not buggy or stuff like that. But like, who develops like the compiling for the Solidity language? Like, who's in which realm is this? Like, is it like open source deployed and you can see like the compilers and everything?
Yeah, so everything is open source. So the Solidity compiler is open source. I think the Ethereum GitHub has already 13,000 commits or something like that. So yeah, so everything is open source.
Because a bug in the compiler itself could also be really costly, right?
Yeah, so I think the current compiler version is 0.24. So actually what we didn't do here, but what you should always do when you program stuff in Solidity is actually name the compiler version you want your code to compile with, so that you don't break or introduce some backwards compatible breaks if you use a newer compiler to actually deploy the stuff later, or a fix of it. Yeah.
Hi. I also have two questions, actually. So the first one is regarding Populus. Is it actively maintained right now? Because I used it a while ago, and it was, as you mentioned, hard to install. And then as you were using it, there were also some kind of dependency errors and so on. So what is the status right now?
So as far as I know, it's actively maintained. So I think recently, half a year ago or so, they transferred the ownership to the actual Ethereum Foundation. So now Populus is part of the Ethereum GitHub repository. So yes.
And also the second question would be, so when you are interacting with the actual contract, what do you normally use? You still use Populus for that? Or is it let's say, Web3 Pi you can also use? Or how do you do it?
So let's assume that it is deployed to the blockchains, and then of course I wouldn't use Populus anymore, but unfortunately something like JavaScript to actually access it, and then there's a Web3 library, which is like the new internet, and you can use that then in JavaScript to actually connect to the to your application on the blockchain. And you can see on my GitHub profile how I did it, although again I'm not a JavaScript developer, so it might actually look like horrible to the expert's eye, but I managed to actually get a website talk to my application.
But for the last question. For the deployment itself, you use Populus then?
So for the stuff actually I did, because it was not so big, I used this Remix IDE to directly deploy it, because then you can immediately play around in Remix and send transactions to it. And of course, especially when you start deploying stuff to the mainnet, you would of course first deploy it to the testnet, and there Ether is basically for free. There are like lots of ways to get free Ether there, and then you can test stuff. And the nice thing about Remix is you can immediately call functions of your contract and see if it behaves the way it should in sort of like an end-to-end testing fashion.
Any questions?
Hi, thanks for the nice explanation. I'm wondering about mechanisms to prevent malicious code. You mentioned a few examples. So what, for example, would prevent me from releasing lots of contracts to have miners calculate prime numbers?
That's pretty good. Very good question. So the problem with everything you deploy and all the computations, they do not come for free. So there's a whole concept of gas on this blockchain, so which I spared out since I only have half an hour. But pretty much every computation you do on the blockchain, you have to pay in the end with Ethereum. So if you do lots of computation, let's say you do a while true, then you have to pay for it. And there's a maximum amount of money that you can pay. So your while true is just going to be a very expensive way to like burn money, and then it fails at some point. So it doesn't run forever. Yeah.
So thanks again. No more questions, right? So I should say two things, like there will be lunch soon, A, and B, there's the retro computer from the keynote in the morning, like the Cobra, set up in the room, the next room here, and you can play some retro games there, like the Manic Miner or something, kind of Bitcoin, no? No.